This training module will introduce you to the technical principles of the basic transmitter. Learning objectives. Upon completion of this module, you will be able to describe what are the pressure transmitter's main components and their relative functioning. Understand what are the 4 different sensor technologies. Explain pressure transmitter related terminology. Summarize the diaphragm seal's working principles and configuration and give details of the main characteristics. Describe manifold functions. Many techniques have been developed for pressure measurement. Inside today's industries, these measurements exploit essentially 2 different pressure instruments. Manometers, commonly used pressure measurement devices generally based on a Bourdon tube that once pressurized produce movement of the indicating needle. Pressure transmitters are devices that convert the physical input into an electrical standardized output signal and send this value to the control room as analog 4 to 20 milliamp and or in digital form according to different communication protocols. HART, Field Bus Foundation, Profibus PA, Modbus and wireless. More advanced pressure transmitters can also provide other diagnostic functions, which tell the working status of the transmitter. Back to the past. Many years ago, the most common type of pressure transmitter was pneumatic, converting the physical input into a physical, proportional air or gas pressure signal. Today, this technology is used only in few cases, such as those in which electrical energy is not readily available. The picture shows the main components of a typical differential pressure transmitter. As you can see, there are 2 main components, top works and bottom works. The bottom works is the most important part of the transmitter, since it's in contact with the process and includes the process flanges and the transducer. These parts can be manufactured in different materials according to application requirements. The top works features the transmitter housing, the terminal block, the communication board, and, if requested, the digital integral display. Its task is converting the process variable. The bottom works is in contact with the process. The top works converts the process variable. The process fluid comes in contact with transducer diaphragms and pressurizes the filling fluid inside the hydraulic circuit of the transmitter. This pressure goes directly to the sensor that is connected to the front-end electronic module, also called primary electronic, converting the physical variable into an electrical signal. The most common sensing methods used today are piezoresistive, capacitive, inductive, and silicon resonant. Before entering into the description of the various types of sensors, it's worth mentioning that over the years, the discussion on the technical superiority of one technology over the others has reduced its importance. The reason is that with present modern manufacturing and compensation technologies, the differences, although existing, are negligible from an application viewpoint. The only exception is the variable reluctance type, which is no longer used by main vendors. A difference in pressure between the 2 sides of the silicon diaphragm produces the sensor diaphragm deflection. The Wheatstone bridge circuit on the diaphragm measures this deformation and generates a variation in resistance. This variation has to be converted into an electrical standardized output signal. The Wheatstone bridge-based sensor works as a result of variation in resistance. The capacitive sensor is generally characterized by a ceramic diaphragm. The diaphragm deflection is proportional to the pressure received from the process. The pressure increase causes the diaphragm to bulge, thus changing the distance between the diaphragm and the reference plates. This distance has to be converted into a standardized output. The ceramic sensor works as a result of variation in distance. The pressure applied on transducer separating diaphragms acts on a sensor diaphragm that divides the sensor into two chambers, where inductance sensors are located. The deflection of this diaphragm causes a difference in inductance frequency that has to be converted into a standardized output. This sensor works as a result of the difference in frequency of the two inductances. The sensing element consists of two H-shaped bridges applied on one side of the silicon measuring diaphragm. The pressure stress deflects the silicon, which causes a change in frequency of the two H-shaped bridges. The output comes from the translation into a standardized signal of the frequency difference between the two bridges. Sensor range. The sensor range is the difference between the highest and the lowest values between the limits within which a quantity is measured. Lower and upper range limits, LRL and URL. The lower and the upper range limits are respectively the lowest and the highest quantities that a transmitter can be adjusted to measure. Lower and upper range values, LRV and URV. The lower and the upper range values are respectively the lowest and the highest quantities that a transmitter is adjusted to measure. Minimum span. The minimum span is the lowest calibrated value resulting from the difference between URV and LRV. Turn down, also called rangeability. The turn down of a transmitter is the ratio between its URL and the minimum recommended span. It represents the capability of the transmitter to cover several pressure ranges without deteriorating the transmitter performance. Maximum working pressure. It is the maximum pressure the transmitter can withstand without any damage. Accuracy. According to IEC 60770-3 and IEC 61298, accuracy is basically the difference between the result of a measurement and the conventional true value of the quantity being measured. In order to express this performance value, it is necessary to carry out three measurements in upward and downward directions at 10% and 20% intervals. Working limits. Pressure transmitters can be used within certain operative limits. Temperature limits, ambient, storage, and process. Pressure limits, overpressure, static pressure, and proof pressure. Environmental limits, humidity, vibration, shock, hazardous areas, etc. Response time. The response time is described by means of a time constant, i.e. the amount of time required for an instrument output to reach 63% of the value it will ultimately reach in response to a step change in input. Normally, an instrument will reach 99.9% of full response within a length of time equal to 4 times the time constant. Okay, you've seen a lot of facts and information, and I'm sure a lot of it isn't new to you. So what have you learned so far? Pressure transmitters are the most common instruments used inside different industries that convert a physical input, pressure, into an electrical standardized signal, 4 to 20 milliamps, according to specific communication protocols. Transmitters are composed of bottom works, flanges and transducer, and top works, housing, communication board, terminal block, and HMI. Today's manufacturers exploit different sensor technologies. Piezoresistive, the Wheatstone bridge-based sensor, capacitive, ceramic diaphragm sensor, inductive or variable inductance, and silicon resonant, H-shaped bridges on a silicon diaphragm. Sensor-related terminology: range, LRL-URL, URV-LRV, minimum span, turn down, MWP, accuracy, working limits, and response time.